Hello dear EAPCET aspirants, welcome back to NEET WORLD. So we will be discussing equilibrium continuation to the last session. So where we have covered applications and also finding the equilibrium constant value by looking at the reactions. Okay, it means for example a chemical reaction is given. So what is the concentration of reactants and products when it is attained equilibrium? By looking at those values, we have calculated equilibrium constant values in the last class. Right now, along with that, characteristic properties of equilibrium constant and how it will be changed, all these things we have discussed in the last class. Right now, so in this session, we will be discussing Le-Chatelier's principle, one of the very important topic of this equilibrium chapter. Along with this particular equilibrium chapter, it will be useful in other parts of chemistry also. Okay, so it is very important to understand Le-Chatelier principle in very proper correct order or correct manner. Okay, so I am going to explain that in very clear crisp manner. Just follow the session till the end, because we will be solving the PYQs once after discussing this Le-Chatelier principle. Okay, right. I hope you have watched the last session and you have cleared all your doubts in those discussion right now. Right. So let me show you this Le-Chatelier principle first. See, what do we mean by Le-Chatelier principle? For example, I am taking an equilibrium reaction. Let us say A is a reactant which is in equilibrium with the product B here. Okay, so let us say this is a equilibrium reaction. Now what happens at an equilibrium? Rate of forward reaction will be equals to rate of backward reaction. Right now, rate of forward and rate of backward reactions are equal. Okay, so now look at this. Now if the state, see at this equilibrium state, if any external stress is applied, for example I am applying a stress on this reactant side. What do we mean by stress here? It can be concentration, or it can be pressure, or it can be volume change or density. All these things comes under stress here. See, for example, in order to understand, I am saying the concentration of reactant A is increased. Now what happens? So if we increase the concentration, since equilibrium state is a very stable state, now what happens is when we increase this concentration, this equilibrium will get disturbed, therefore it will move forward. So after moving forward, what happens? Whatever the increment in concentration on this reactant side will be readjusted by sending the equilibrium state towards forward. Right now, again that will be readjusted, therefore it will get its again new equilibrium state will be obtained. Okay, so I hope it is clear. For example, this pen is there. Okay, to that what we are doing, see I am applying some stress over here. So it is, see it is bending to this much extent. See again it become constant here. Why? Again this is the equilibrium state for this particular pen, I can say. Okay, so again now if I increase the stress from downside, now what happens? Now it is bending this side. So this again after bending this much extent, it is stopped here. It means to some extent it is went this side and now it is stopping, means again this is a new equilibrium state. This is how you can understand what exactly mean by equilibrium. See, if I increase the concentration of product, what happens? The concentration of product is increased, it means stress is on the product side. So now if you increase this concentration, then what happens? Equilibrium moves forward, that's it. Now one more in a different way, in an opposite way also I can say. See, if concentration of A is decreased, now what happens? Since concentration of A is decreased, then equilibrium moves backward, therefore its concentration readjusted, concentration of AB will be readjusted, again they attain their equilibrium, like that. See, if a stress is applied to a system in equilibrium, the equilibrium for a time being get disturbed. As a result, system moves in a direction which tends to relieve that external stress, and finally a new equilibrium is attained. See, if any stress is applied, therefore equilibrium shifts in a direction to nullify or to cancel out that external stress, that's it. This is a very simple way to understand. And now what are the factors affecting on this equilibrium? First factor is concentration. Okay, simple, we discussed now concentration, how it will be affecting reactant side, product side if I write. Okay, if reactants and product side are written. So if we increase the concentration of reactants, if concentration of reactants are increased, now what happens? If concentration of reactants are increased, equilibrium shifts forward direction. Okay, forward direction. If concentration of reactants are decreased, now if concentration of reactant is decreased at the equilibrium, then this equilibrium shifts backward to increase the concentration of these reactants. Okay, therefore they will nullify that whatever the external stress applied, and they will establishes the equilibrium. That's it. Okay, and again, if concentration of product is increased, it means what? This concentration is increased. If it is increased, then equilibrium goes backward. Right now, equilibrium shifts backward direction. Okay, if concentration of product is decreased, if this concentration is decreased, then equilibrium moves forward to nullify that, and equilibrium shifts forward direction. That's it. This is the effect of concentration. I am going to show you the questions how simple on this particular topic just in few minutes. Okay, and the next effect of second thing, effect of temperature. Effect of temperature. For example, I am giving you formation of ammonia in Haber's process. Okay, so this is an exothermic process. What I am saying, this is an exothermic process. It means heat is released during the reaction. So it means heat is released during this formation of ammonia, means the formation of ammonia is favored by releasing of heat. This releasing of heat we can say exothermic reactions. What is that? Exothermic reaction. So if heat is released, I am saying exothermic. If it is exothermic, see, heat is released means what about its internal energy, I mean energy of the system decreases now. It means the forward reaction, which is for an exothermic reaction, the forward direction will be favored by lower temperature. So low temperature favors forward direction for exothermic reactions. Okay, and the next, if forward reaction is exothermic, then backward will be endothermic. Okay, so what I am saying, for this backward will be endothermic. So simply you can say low temperature favors forward reaction. Okay, and high temperature favors backward reaction. Why backward reaction? See, backward is endothermic I am saying. Endothermic reactions requires absorption of heat. By absorbing the heat, they will move forward. So absorption of heat is nothing but increasing the temperature now. So if we increase the temperature, that will favors backward. Okay, hope this is clear. Right, next, the next thing is here, effect of temperature on this equilibrium constant values can be given using this formula. Log K2 by K1 is equals to delta H by 2.303 or 1 by T1 minus 1 by T2. Okay, so again here, what is K1, K2? K1 is the equilibrium constant at temperature T1 and K2 is the equilibrium constant at temperature T2. Okay, that's it. So now for an exothermic reaction, these conditions are important. For an exothermic reaction, see, we know for exothermic reaction, temperature, final temperature should less than initial temperature. It means that will favor forward. So if T2 is greater than T1, then K2 will be greater than K1. This is for which one? Exothermic. See what I am saying, exothermic reaction now, low temperature favors forward, but T2 is greater I am saying. If T2 is greater, what happens? High temperature, no? So high temperature means it will goes backward, therefore K1 will be greater than K2 it becomes. Okay, and if T2 is less than T1, now T2 is less now, it means for forward exothermic reaction, final temperature is getting decreased. If it is decreased, it means reaction favors forward. So I can say here K2 will be greater than K1. Okay, this is in which case? It is in exothermic case. Okay, and this is important. You can expect a question like this based on this. And the next, for an endothermic reaction, endothermic reaction. See, endothermic reactions are favored by high temperatures. It means T2 if greater than T1, then what happens? K2 will be greater than K1, that's it. Okay, but if it is in reverse manner, T1 is greater than T2, then K1 will be greater than K2. Okay, these are the things you should remember. And after this effect of pressure, an equilibrium reaction. See, there are three conditions you can take. Effect of pressure will be seen in three ways. So, the effect of pressure will be observed only in case of gaseous reactants or products are involved, or products must be present. On solids and liquids it won't applicable, because gases have that compressibility but not for liquids and solids. That's why it is applicable only in case of gaseous reactants and products. Okay, then next look at this. See, I am writing something like formation of ammonia only. I am writing N2 plus 3H2 gives rise to 2NH3. This is one condition, and other I am making three conditions, just try to understand this. And H2 plus I2 gives rise to 2Hi. All of them are gases only. And the next, PCl5 undergoes decomposition to give PCl3 plus Cl2. Okay. So these are the three reactions. All of the reactants products are gases only here. Tell me here what happens in this case. Just try to find delta Ng in all these cases. Delta Ng is how much? 2 minus 1 plus 3, that is 4, that is minus 2. So delta Ng is negative, delta Ng is less than 0. So why I am making this conclusion? It will be easy for you to understand or to remember for later purpose. Okay, so just remember here what I am saying with the concept only. I will tell you, just listen here what I am saying. So here delta Ng you calculate, this is equals to 0, and here delta Ng 2 plus 1, 2 minus 1, that is 1. So that is delta Ng is greater than 0. So after finding this, what I am saying here, see, whenever there is delta Ng 0, there is no effect of pressure, no effect of pressure, you can remember. But when delta Ng less than 0 or greater than 0, there will be effect of pressure on this equilibrium reactions in which gases, reactants or products involved. Okay, so now look at this. Every time effect of pressure will be there more on more number of moles side. It means number of moles are how many here? 4 are there. Gases number of moles are 4. Here are 2. So if we increase the pressure, see, in unit volume, if you take some unit volume which are in equilibrium, the number of moles are more on this reactant side. Therefore, effect of pressure will be more on this side only, because if we increase the pressure, what happens? It will be compresses. Therefore, number of moles present in unit volume increases. So number of moles present in unit volume will be increased more in this this number of moles more side. Therefore, equilibrium shift in a direction to decrease that number of moles. So it means whenever there is delta Ng less than 0, then equilibrium favors forward if I use high pressure. So high pressure favors forward. Okay, forward. It means what? If delta Ng is less than 0, high pressure favors forward. If delta Ng less than 0, high pressure favors forward. If I use only maintains low pressure, then that will favors backward direction. Okay, hope this is clear. If not, just look at this example, you will get more clarity. See here, delta Ng is more at which side? Here we have 2 and this side 1. I mean number of gaseous products are more this side. Therefore, effect of pressure will be seen in this product side. So if I increase the pressure, the number of moles present in unit volume increases. Therefore, equilibrium tries to shift reactant side. Okay, so it means high pressures whenever delta Ng is greater than 0, high pressure favors backward, and low pressure favors forward. That's it. Okay. See, if delta Ng is negative, high pressure favors forward, low pressure favors backward. If delta Ng is positive, high pressure favors backward, low pressure favor forward. Okay. So either you can remember this direct statements, or it is better to understand the concept what I am saying. Whenever there are more number of moles are there, effect of pressure will be more on that side. It means, for example, this is reactant side, try to listen here what I am saying. Reactant and this is product. Okay, all of them are gases only. So now here I am saying there are 4 gaseous products are there, and there are only 2 gaseous products are there in a unit volume. Okay, now what happens, I am increasing pressure. So if I increase the pressure, this is the container in which this equilibrium is established. Now I am increasing the pressure by applying some pressure on this container. Now what happens, it will compress, gas will compress, therefore number of moles present in unit volume increases. So let us say it is becoming doubled, so it becomes 4, it is also becoming double, it becomes 8. Okay, so what is the increase in number here? The increase in number is 2, but here increase in number is 4. It means where do we see more number of moles increment? In this product side. So since more number of moles are increased on the product side, equilibrium will shift in a direction to nullify that. So product side number of moles are more increased, therefore equilibrium moves backward to nullify this greater increment. I hope the concept is involved. So therefore number of moles are more at product side, therefore high pressure favors backward direction, and low pressure favors forward direction for this particular reaction. That's it. This is the only concept you need to remember for complete solving questions of this high pressure or effect of pressure on this equilibrium reactions. Okay, right. Let me show you a few questions, then you feel more comfortable here. Look at this what they are saying. For a reaction, see this is a EAPCET question again. For a reaction given, the favorable conditions for the reaction to occur in the forward direction are, see, during the reaction heat is released. If heat is released during the reaction, we are saying exothermic process, right now exothermic process. So if this forward reaction is favored by releasing of heat, how I am saying, because equilibrium comes forward with releasing of heat now, so forward reaction is favored by lowering its temperature or lowering its heat. So low temperatures favors forward direction. Okay, and when it comes to effect of pressure, so look at this, forward direction, low pressure, low temperature. So you can remove these 2 options. Okay, and then next pressure. What is the pressure effect? I told you, number of gases, product and reactants you check. How many gases products are there? 1. Gases reactants are how many? 1 plus 1 by 2. It means number of moles of gases reactants are more now. So if I increase the pressure, the effect will be seen on the reactant side, therefore equilibrium moves forward. So high pressures favors forward direction. That's it. Second option will be your perfect answer. See, nothing, no formula substitution, nothing, just understand the theoretical concept involved here to solve this kind of questions. Okay, right. Now answer me this one. The formation of ammonia from its constituent elements is an exothermic process. If it is an exothermic process, we know low temperature favors forward. The effect of increase in temperature or equilibrium will be, if the temperature is increased, now what happens? See, low temperature favors forward reaction right now, but effect of temperature on increasing the temperature on the reaction equilibrium. So what happens? If temperature is increased, reaction goes backward. So backward reaction is favored. So fourth option will be your answer for the question. Okay, right. This is also clear, I hope. Next, look at this, what they are saying. Le-Chatelier principle is not applicable to. So 4 options are given, to which option it is not applicable. So H2 plus I2 gives rise to 2HI. So okay, this is a gaseous reactants and products are involved, but here if you see solid iron, solid sulfur and solid product. So all of them are solids now. So here you cannot use Le-Chatelier principle. Okay, so option B will be your answer for the question. Okay, next. Try to answer me this one. Try to answer me this one. So anyone in the chat box can answer me the same question which I am projecting on the screen. Yeah, so what they are saying, see, in which of the following reactions at equilibria, the position of equilibrium shift towards product if the total pressure increased. It means high pressures favors which direction they are asking, which direction, forward or backward they are asking. What I told you, if gaseous number of moles of products are more, equilibrium moves backward. If gaseous reactants are more, equilibrium moves forward on high temperature. So just look at this, see 1 gaseous reactant and 3 gaseous reactants, total 4 this side, 2 this side. So reactants, gaseous reactants are more, if I increase the pressure, equilibrium moves forward, that's it. So they are saying following equilibria, the position of equilibrium shifts product side. So first option is perfect. Next, second option you can see 1 gaseous reactant, second gaseous reactant, this side also 2. If delta Ng is 0, what I told you, there is no effect of pressure right now. So this is no effect. Next 1, 1, this side also 2. So total 2 minus 2 are there. So here also 0, there is no effect of pressure here. Only first option will be a perfect answer for the question. Right now, hope this is clear. Right. Let me discuss few more applications of Le-Chatelier principle so that we will get complete idea. So till now what we have discussed, effect of concentration is over, then next effect of pressure is over and effect of temperature is also done. Next, effect of catalyst. See, there is no effect on equilibrium by this catalyst, but it makes reaction to happen, reaction to like it makes reaction faster, therefore equilibrium achieves very sooner. It means very fast equilibrium will be achieved with the help of this catalyst. Okay, this is the application of catalyst you can say. And when it comes to inert gas, so addition of inert gas or effect of inert gas on equilibrium. So what do we mean by inert gas here? That gas should not involve in any chemical reaction with the equilibrium species. It means, for example, ammonia reaction is there. So in that, if I add inert gas, what happens to the reaction? So like that, let me take few examples and let me explain you. Like this I am taking. Okay, other ways, whatever the examples we have considered previously, same examples I am taking here so that you will get more clarity on chemical reactions itself. See, first one here, N2 plus 3H2 gives rise to 2NH3, and here H2 plus I2 gives rise to 2HI, and then next here PCl5 decomposes to give PCl3 plus Cl2. All the things are gases only you consider. So again, effect of volume on solid and liquids are not considered here. Only gases, reactants and products should be there. Okay, right. effect of inert gas will be seen on this gaseous particles only. Okay, and here whatever I am saying here, when we add inert gas, will they participate in chemical reaction? No, right? So initially let us say this is the volume of the container, equilibrium container is this much. Now when we are adding this inert gas, what we are adding? Inert gas is added. So what happens? The volume of the container will expands because inert gas is added now. So therefore its volume becomes like somewhat here. So initially at here, now it is increased, the volume is increased. So by this what I can say, the number of molecules, this reactants and products molecule present in unit volume decreases. Right now initially here these products are 2 but reactants are 4. So now what happens when we increase the volume, the number of reactants and products in unit volume decreases. Okay, here also you can understand, upon adding this inert gas, if volume is increased twice, what I am saying, if volume is increased twice, or I can say the number of gaseous particles in unit volume decreased by half, means it is becoming 1 and it is becoming 2. Half means this one only, 2 to 4 to 2, 2 to 1. So what is the decrement here? 2 particles are decreased. What is the decrement here? 1 particle. So where do you see more decrement? So when inert gas is added, the volume change will be more on this reactant side. Therefore more decreased in the reactant side now. So if it is more decreased, equilibrium shift to increase the decrement. Therefore equilibrium favors backward. Okay, so whatever I explained till now about this inert gas, addition of inert gas, this is at constant pressure. What I am saying, at constant pressure. So if delta Ng is less than 0, addition of inert gas favors backward. Where it will favors? Backward direction. Why? See, number of moles are more here. If we increase, if we add the pressure, if we add this inert gas, number of moles in unit volume decreases here more. When here it is 2, here it is 1. It means here decreased is more now. Therefore equilibrium favors backward. Okay, hope this is clear. Now if there is delta Ng is equals to 0, then no effect of inert gas. Okay, and here delta Ng is positive right now. So again number of moles decreased will be more on this more number of moles side. This is 2, this is 1. So decrement will be more on this side, therefore equilibrium moves forward. So addition of inert gas favors forward reaction, that's it. Okay, so this is the way of like understanding the concept. I hope it is clear without any confusions. Now what I told you, whatever the discussed thing is there, that is at constant pressure. So at constant volume, if there is no change in volume, at constant volume, if I say constant volume, so at constant volume there is no change in this volume, not like expansion, compression, no not taking place now. Therefore no effect of addition of this inert gas. Even if we add inert gas without having any change in this volume, therefore there is no effect, because number of gaseous reactants and products present in unit volume will remains same if there is no expansion or compression. Okay, right. So try to answer me this question again, what they are saying. Observe the following equilibrium and try to answer that addition of aqueous oxalic acid solution to the above equilibrium. What happens to the above equilibrium? See, we have deep red color product and yellow color reactant and colorless SCN minus ion. So now what happens? Addition of oxalic acid. See, oxalic acid will form a complex with this Fe+3 ion. Therefore the concentration of this Fe+3 ion decreases now, because it is completely consumed by this oxalic acid. As concentration, as this Fe+3 ion is consumed by this oxalic acid, its concentration decreases on this reactant side. right? Now if it is decreasing in the reactant side, equilibrium moves backward to increase this Fe plus 3 ion concentration, right? So if it is moving backward, the deep red color intensity decreases. What happens? Deep red color intensity decreases. So you can see, where do we have equilibrium shift towards formation of no. Next, deep red color increases, no, decreases it. Intensity of deep red color decreases. That's it. Option C will be a perfect answer, because reaction favors backward. Therefore this complex dissociate to give the initial reactants and this species, reactant species. Okay, so option C will be your answer for the question. Okay, next, I hope this is clear. Can you answer me here? Observe the following equilibrium where H2 plus I2 gives rise to 2HI. Which one of the following does not disturb the above equilibrium? Tell me, what will be your answer for this? Just now we discussed about this, very clearly we discussed. Yeah. Which one of the following does not disturb the above equilibrium? Tell me. See, if you see, if I increase the concentration of reactants, equilibrium moves forward. Or if I decrease the concentration of reactants, equilibrium moves backward. If I increase the concentration of product, also equilibrium moves backward. If I decrease the concentration of product, equilibrium moves forward. These are the things are there. So see, addition of H2, it means concentration of reactant is increased. There will be effect. Okay, disturbance happens in the equilibrium. Removal of HA also causes equilibrium disturbance. Addition of I2, this is also causes a disturbance in equilibrium right now by moving forward. So it means if you look at this fourth option, addition of helium gas. Helium gas is an inert gas now. Noble gas is, right, inert gas that won't participate in chemical reaction, but that will changes the volume by expansion or compression. Right now it will expand this volume when we add. But I told you that if there is no change in number of gaseous products formed and reactants involved, then there is no effect of inert gas. So how many gaseous products are there? 2. How many gaseous reactants are there? 1 and 1. So you can say 2. So this will be 0. If delta Ng is 0, there is no effect of addition of inert gas. In all three other cases, A, B, C case, there is some effect, but in D case, no effect. So option 4 will be your answer for the question. Okay, right. Next, these are the some important questions that must be followed or understood for every aspiring student of like EAPCET or whatever the other exam you are preparing. Okay, so now let me give you some other model questions. See, look at this question. This is from again EAPCET only. Try to answer me this. When 1 mole of reactant A and 1 mole of B were heated in 1 liter flask, 0.5 moles of C was formed at equilibrium. What will be the equilibrium constant Kc for the given reaction? Okay, so see what they are saying, initially at the beginning of the reaction, at the beginning of this reaction A plus B is in equilibrium with C plus D. At the beginning of the reaction T 0, so 1 mole of A, 1 mole of B they have taken, and at the beginning there will not be any product. But when this equilibrium is attained, it means time when it is reached at equilibrium, T equilibrium I am saying. So amount of C formed is 0.5 they are saying, that is nothing but 1 minus alpha, 1 minus alpha, this is alpha, this is also alpha. So what is the value of alpha? They are saying this is 0.5 here. So it means 1 minus 0.5, this can be also 1 minus 0.5, then this is 0.5 remaining, here also 0.5, here also formed is 0.5, that's it. Okay. So Kc, equilibrium constant, can be written as concentration of products by concentration of reactants. So what is the concentration of products we have? C and D, 0.5, 0.5, and reactants we have A and B, that is also 0.5 into 0.5. So all concentrations of reactants and products are same now, so everything cancel out and we will have a Kc as 1. Okay. So option C will be your answer for the question. Okay, right. Yeah. So I hope you got complete idea on Le-Chatelier principle that we have discussed, because you can expect maximum probability to get one question from this equilibrium, particularly on basis of Le-Chatelier principle. Okay, and understanding buffer solutions, common ion effect, all these things includes applications of Le-Chatelier principle only. Okay, right. Look at this. Which one of the following expression is correct for delta G? Okay, so remember Gibbs free energy is there now, delta G will be taken as delta Z naught plus RT ln Q. Okay, Q means reaction quotient. So at equilibrium, if I say reaction is at equilibrium, then delta G value becomes 0. What I am saying, delta G value becomes 0. If this value is becoming 0, you can send this here. So what happens, delta Z naught will be equals to minus RT ln Q, that's it. Ln Q becomes K, because it is at equilibrium now. So at equilibrium, QC is called as Kc. Okay, this is other than equilibrium states, you can say reaction quotient. At equilibrium state, you should call it as equilibrium constant. Okay, K. So where do we have that kind of option? The first one. Okay, now they will ask what is the value of K by giving delta G and temperature, everything. So what you can make, K is equals to minus delta G by RT e to the power this thing. Okay, they may ask in terms of logarithm also, like K is equals to 10 power minus delta G by 2.303 RT. This will be in terms of logs, mean 10 we will get as a base. Okay. So this discussion is over, right. So next thing we need to discuss now the things related to ionic equilibrium. Okay. So let me give you some basic idea on ionic equilibrium. Yeah, ionic equilibrium. So before discussing this, just tell me, those who are watching this session, like, are you effectively preparing? If you are really preparing for your upcoming EAP set more effectively, so you need to solve at least some 30 questions at the beginning per subject. Every subject you try to solve 30 questions. Okay? Why? Because the more the number of questions you practice from a chapter or on a topic, and that all question must be having maximum difference, like different model questions should be solved, not of one type question or one model question. All different model questions must be practiced, then you can easily score maximum marks in the exam. Because if you practice all the model questions that are appeared till now in the final exams, like in EAPCET or JEE or NEET, then definitely there is maximum probability to come only from those model questions. Okay, so just try to take one EAPCET or any PYQ book, try to solve different model questions, like you just collect the EAPCET previous year questions. Okay, and if you are looking for EAPCET previous year questions, just go through our playlist itself. That playlist contains like lot of PYQ questions, because we covered 20-25 2025 AP EAPCET papers are covered from our side. 2025 AP EAPCET papers are covered. Okay, and for 2024 also covered. Okay, right. There are many PYQ sessions which we have did previously also. You can use them very effectively for making preparation for your EAPCET 2026. Okay, right. So whenever you wanted to attempt or to solve only PYQs, just watch these sessions and make use of it for your EAPCET 2026. And still, if you want few more questions like EAPCET previous year papers, you can join our Telegram group. The link will be provided in the description box. If not, you just mention in the chat box. Our team will respond to that whenever you mention in the comment box. Okay, or there will be like our Instagram ID also. You just send a message on that. The team will share you the previous year questions or whatever the things you are expecting from us. Okay, right. Right. So now ionic equilibrium. What exactly ionic equilibrium means? See, I told you there are two types of equilibriums, like normal chemical equilibrium and ionic equilibrium. So before these we have seen reactions involving without any ions, like formation of ammonia or formation of HI which is a molecule from its respective species like H2 and I2. So there is no involvement of ions. You can simply call it as chemical equilibrium. Now those equilibrium reactions in which ions are involved can be considered as ionic equilibrium. Okay, so what we need to know, there are some ions involved in the equilibrium reaction, then those reactions are called ionic equilibrium reactions. Okay, so now how these ions are formed? Yes, to understand that you need to know what is this electrolytes. Okay, so what are these electrolytes? So those substances which allows passage of electricity through those electrolytic solution, those its solutions I can say. So if I take any solution of a particular electrolyte, it has an ability to pass current or electricity through it, can be considered as electrolytic solution. So these electrolytic solutions or electrolytes are of different types, like I can say weak and strong. So strong electrolytes which has 100% dissociation, degree of dissociation should be 100%, then we can say it as a strong electrolyte. So what comes here? All the strong acids and strong bases and salts comes under these strong electrolytes. Okay, and weak electrolytes here, so which has only partial dissociation or lower extent of dissociation, like I can say less than 100% dissociation, then we can say them as weak electrolytes. Okay, so generally all weak organic acids or weak organic bases, okay, comes under this weak electrolytes. Okay, and along with these there are some salts which are having very low solubility. Those are generally covalent salts like AgCl, those things. So I can say sparingly soluble salts, soluble salts. These are the examples of weak electrolytes. Okay, so now tell me HCl, NaOH, CaOH twice, all these are comes under strong electrolytes, and salts like formation of a strong acid and strong base and a weak acid as a strong base. These things, all the salts comes under strong electrolytes. Okay, and weak acids you can say acetic acid and ammonium hydroxide. These are the weak bases, weak acids which comes under weak electrolytes case. Okay, and sparingly soluble salts, something like BaSO4 or I can say AgCl, AgBr, this comes under weak electrolytes. Okay, and then next Ag2, Cr2O4, this comes under weak electrolytes. Okay, right. So let me discuss a few more things. So what I am saying, that depends upon electrolytes, classification of electrolytes depending upon the degree of dissociation. If 100% dissociation, strong electrolyte. If only partial extent of dissociation, less than 100, it might be 40%, it might be some 60%. So consider them as weak electrolytes. Okay, all organic acids, organic bases comes under weak electrolytes here. Okay, these are the generalized statements to understand. Okay, and the next, now take any weak electrolytes again. See, now we have discussed strong electrolytes, weak electrolytes. Now, strong electrolytes, weak electrolytes. So now ionic equilibrium will be seen in this case, in weak electrolytes case, because strong electrolytes, if I take HCl, it will undergo 100% dissociation. There is no meaning of saying that it will be having equilibrium right now. So now if I take acetic acid here, yes, it will dissociate as CH3, COO minus and H plus. Yes, here some meaning is there because it will be having partial dissociation. It means what? If I take initially only acetic acid is taken, so it has having concentration C. There is no ions formed at the initial because only acetic acid is there. After some time, what happens? Some amount of reactant converts into its ions. So I can write that C minus, the degree of dissociation here as C alpha. Okay, so alpha is the degree of dissociation of this particular compound having concentration C. So C multiplied with alpha. Alpha indicates what? How much amount of this acid undergone dissociation. Okay, that is what degree of dissociation. Now, whatever the ions I have mentioned here coming from this acid only now. So this ion will be having the same concentration as amount that is decreased here. That is decreased is how much? C alpha. Same this one also having C alpha. Okay, and after this I can write something called degree of dissociation. After writing this, you can say acid dissociation constant. If it is an acid, acid dissociation constant. If it is a base, base dissociation constant. If it is a something normal compound, you can say dissociation constant of that particular compound. Okay, so Ka I am saying for this, or if you want to say, just say it as equilibrium constant Kc. Okay, so equilibrium constant Kc means the concentration of products multiplied product of this concentration of products by concentration of reactant. So that is nothing but acetate ion concentration, here H plus ion concentration by acetic acid concentration, like this. So this will be, what is the concentration I have given here? C alpha, and for this one also C alpha, and for acetic acid it is C minus C alpha, that is 1 minus alpha I can write. Okay, this C cancel, we have C alpha square by 1 minus alpha, which is nothing but our Kc. Okay, and if it is a weak electrolyte having very less dissociation, it is having less than 10% if I say, then what happens? Kc will be equals to C alpha square. Since this alpha value is very small, 1 minus alpha I can write it as 1. Okay, therefore Kc becomes C alpha square. From here the degree of dissociation can be written as Kc by C, where Kc indicates equilibrium constant and here C indicates concentration of that particular electrolyte. Okay, so now this is one of the important thing to be remembered. Okay, so now what it is saying, alpha means a degree of dissociation, which is equals to root over Kc by C. It means what? The degree of dissociation of a weak electrolyte increases if I decrease the concentration. If concentration decreases for that weak electrolytes, its dissociation increases. So it means upon dilution, means what? The decrease in concentration. Now see, I have 1 molar solution, so I can make it as 0.1 molar by adding water now. So that is nothing but dilution. So upon dilution, the degree of dissociation alpha of a weak electrolyte by dilution. Upon dilution, alpha, degree of dissociation of weak electrolyte increases. If C decreases, that is if concentration decreases, degree of dissociation increases. It means for understanding purpose, look at this question. I have 0.1 molar acetic acid and I have 0.5 molar acetic acid and 0.1 molar acetic acid. Tell me, alpha will be maximum in which case, degree of dissociation will be maximum in which case? The degree of dissociation will be maximum in which case? Out of these 4 options, 3 options. See, lower concentration, maximum degree of dissociation. So, alpha will be more in this 0.1 concentration. If I say A, B, C as options, so C will be having maximum alpha and the next B and least is for A. Okay. So, based on this Ostwald's dilution law or Ostwald dilution principle. Okay. Right. Next, if I say 1 molar NaCl, 0.5 molar NaCl, can you answer me for this? No, you should not use this degree of dissociation and concentration relation in case of strong electrolytes. It is applicable only in case of the weak electrolytes, not in this strong electrolytes. Okay. So, here 100% dissociation, almost 100% dissociation will be there in case of strong electrolytes. Okay. Right. It will not, Ostwald dilution principle is not applicable in case of weak electrolytes. And you can see one more relation I can create from here. See what I am saying, concentration, which is nothing but molarity only now, that is given as number of moles by volume. If I say 1 mole, then 1 by V it becomes right now. So, in the place of C, I can replace with V, so that it becomes C alpha is equal to root over Kc by, in the place of C I can write 1 by V, 1 by V, that is nothing but here V. So, alpha is directly proportional to root V. It means if I increase the volume of solution, its degree of dissociation increases, that is it. Okay. So, this is the application of Ostwald dilution principle in case of weak electrolytes. Okay. And in the next class, we are going to cover this type of questions like what is acid base theories, how many types of acid base theories are there. Okay. If there is any blur, just inform me once. Yeah. How many types of acid base theories are there? So, based on that, what type of questions? See, this is a question that we can see. Okay. And pH calculations, and what is a common ion effect, we have buffer solutions, buffer action. Okay. All these things will be discussed in the upcoming session with inclusion of proper quality PYQs of EAPCET or if possible JEE and NEET exams also. Okay. So, you just click on the subscribe button, stay connected with this NEET World channel, and until that time just practice some questions related to today's discussion, and if you haven't watched the previous sessions, just go watch them and you can make your preparation more productive. Thank you for watching, stay connected.